So I just finished teaching a course in abstract algebra, and I was reminded of this nice problem that happens near the beginning of the class. You classify all groups of order 4 without any of the machinery or the results that you learn in the middle or later parts of the course. And I think that's a really nice problem because it doesn't really require much previous knowledge, and it's kind of fun. So I thought that's what we do today, and I thought we could call this like small algebra because 4 is a fairly small number. But before we do that, I'd like to recall a definition and then look at some examples of this definition. So a group, G, is a set together with an operation. We'll call that operation star. And what it does is it takes two elements from G, combines them, and gives you a new element from G. And star must satisfy three axioms. First of all, there has to be what we'll call an identity element. And we'll call this 1. And this identity element, well, it does exactly what you'd think it should do, and that is nothing at all. So 1 combined with G is the same thing as G, which is the same thing as G combined with 1. Now notice I'm pointing out that these might be different. Well, in this case they're not, but we don't have to have commutativity here. And then not only do we have to have an identity, but we also have to have inverses. And what is an inverse? Well, it's a path back to the identity. We could write that out like this. So for every G in G, we can find something that we'll call G inverse, which is also in G, so that if we do G star G inverse or G inverse star G, we get back to 1. And so you probably know about the multiplicative inverse in the rational numbers or the real numbers. Well, this is just like a generalization of that. And then one more thing that we need is associativity. So in other words, if we have A, B, C, and G, if we do A star, B star C, we get the same thing as A star B star C. And let's just underscore again that we don't need commutativity here. All right, so I'd like to look at some familiar examples before we look at our main result of the video. So maybe a most familiar example would be if we just take the integers and then our operation is addition. So I think it's pretty clear that the identity is equal to 0. If you add anything to 0, nothing changes. And then inverses are just the negatives of whatever numbers you come up with, and then addition is associative. To really prove addition is associative, you actually have to go to the definition of addition via like a set theoretic setting, but we're not going to do that. And then a relative of the integers would be the integers modulo n. So that's just, well, technically it's the equivalence classes when you look at congruence mod n, but you can really just think about it as the numbers between 0 and n minus 1, where you do normal addition, divide by n, and keep the remainder. So as an example, inside of Z8, if we do 7 plus 7, we get 14. But if you divide 14 by 8 and keep the remainder, you get a remainder of 6. So in this structure, 7 plus 7 is equal to 6. And then 5 plus 4, well, it looks like it'll be equal to 9. But if you divide that by 8 and keep the remainder, you get a remainder of 1. And then 6 plus 2 is 0. Because that's equal to 8, there's no remainder there. So in this case, we would say that 6 and 2 are inverses. And then maybe another familiar example would be all 2 by 2 matrices with non-zero determinant. And here I've just reminded you how to multiply matrices. And I'd like to point out that this operation is not commutative. So it's important to recall or to be aware of the fact that groups need not commute. Okay, so now let's to our main result. So like I said before, in this video, we're going to be exploring groups with 4 elements. Or we could also say exploring groups of order 4. And this may seem like a little silly thing to do, but if you have groups with a certain number of elements, a really interesting question is to classify those groups. And a lot of advanced group theory seeks to do that, classify groups of a certain order. And this is maybe one of the simplest types of problems towards that direction. And like I said before, it won't require any advanced or really even intermediate results. Okay, so let's say our group G has the elements 1, A, B, and C. Well, it has to have 1 because it has to have an identity. And now we'd like to figure out, well, really, what is the multiplication table between A, B, and C? Okay, well, maybe the first thing we could ask is, what do we get when we square A? In other words, when we multiply A to itself. And I'd like to point out that throughout this, I'm going to be using a little bit of a simplified or shortened notation for our operation. So if you have, for instance, inside your group, G star H, we would just write that as GH. Okay, so what is A squared? Well, there are exactly 3 possibilities. A squared could be equal to 1, so that means A is its own inverse. That's totally legal. A squared could be equal to B or C, and those are really the same case because we could just like switch B and C and do them like the same way. Or we could have A squared equal to A, but actually we can't have that because if we left multiply both sides of this equation by A inverse, that tells us that A is equal to 1, but that means that this element and this element are the same, which means we indeed do not have 4 elements. So, like I said, this is impossible. And what we'll focus on in this video is maybe this first case. And we're doing that because you get the same sort of argument out of the second case. It's just the argument comes in a different order. So if you'd like to apply what you've seen today, maybe this would be a nice like homework exercise. Okay, so like I said, we're going to look at this case when A squared is equal to 1. And that brings about the next question, and that would be, what is A times B? So let's maybe write that out. So what is A times B? Okay, good. And now let's spread that out into cases just like we spread into cases what is A squared. Okay, so let's look at this first case. Well, A times B could be equal to B potentially. Oh, but that's actually not possible either. And that's not possible because here we could write multiply by B inverse and we would end up with A is equal to 1. But, baked into our assumptions is that A is not equal to 1. So this is actually not a possibility. Okay, so maybe let's start over. We've got a new number 1. Well, maybe A times B could be equal to A. Oh, but we're going to end up with a fairly similar problem there. So I'll just say no, and that's because here we could left multiply by A inverse, and that will give us B is equal to 1. Okay, so that means that this is also not a possibility. So that's not really number 1 either. So now let's look at a new number 1. Okay, well if A times B can't be A, it can't be B, well maybe it could be 1. So what if A times B is equal to 1? Oh, but this is a problem here too. Let's left multiply this entire equation by A, and that's going to give us A squared times B is equal to A. But let's recall our assumption up here is that A squared is equal to 1, so that tells us that B is equal to A. Okay, well, look at that. If B is equal to A, then we don't have 4 elements. So that is also impossible. Oh, but we've only got one last element for A times B, and that is C. So that means that that's the only possibility. So A times B is equal to C. Okay, so let's put a nice box around this so we can save it for later. And now let's move on to our next question, and that is, what is B times A? So let's recall our multiplication need not be commutative. So that means we have to check both directions of the operation, or maybe orders of the operation. And well, this is gonna fall apart just like the other one did. So let's look at our first case. let's say b times a is equal to a, but notice by right multiplying by a inverse, that tells us that b is equal to 1, and that is not possible. So in fact, that cannot be number 1 in this, line of reasoning. Well, what if b times a is equal to b? Well, you'll see that that's also not possible for a very similar reason to this over here. And then what about b times a is equal to 1? Well, you'll also see that that is totally impossible for the same reason that we had over here. That would imply that b is equal to a again. Okay, well, but that's exhausted all possibilities for b times a except for c. So that brings us to this same result. So that means that b times a is equal to c. Okay, good. Okay, so now let's maybe clean this up and keep the facts that we know so far and then go from there. Okay, so far we've determined if a squares to 1, then a times b and b times a both have to be c. And I think that leads us logically to the next question, and that would be, what happens if we square c? Okay, so if we square c, well, we can write that as c times c, but we can take both of these versions of c. So let's maybe take b times a times b. Oh, but that's equal to b times a squared times b. We actually used associativity here. We used associativity to just like put the parentheses anywhere we wanted. Oh, but a squared is 1. That just gives us b times b, which is b squared. And this breaks down into 2 legitimate cases. And the first case is that b squared is the same thing as c squared, which is equal to 1. So that means every non-identity element squares to 1. And then the second case is the case when b squared is the same thing as c squared, which is the same thing as a. And notice those are all of the cases. And that's because b squared is not allowed to be b, because that means b would be the identity, just like we saw before with a. B squared cannot be c squared, because that's the same thing as c squared being equal to c squared. And then c would be the identity, but that's the same problem that we had when we were looking at values of a squared, like this over here. Okay, so those are our 2 possibilities. Now we need to work with these 2 possibilities to find out what the rest of the products are. Okay, we know a times b and b times a, they're both c. We know everything multiplied to itself here, but we don't know a times c, or c times a, or b times c, or c times b. So let's look at those. Okay, so let's investigate a times c. So what happens if a times c is equal to a? Well, then we can left multiply by a, and we'll get c is equal to a squared. Oh, but if c is equal to a squared, that means c is equal to 1, but that's not possible. Okay, so that means that a times c cannot be equal to a. Okay, well, what if a times c is equal to 1? Oh, but now we can left multiply by a. That gives us a squared c equals a. Oh, but that means that a is equal to c. Again, that's not possible because we wouldn't have enough elements. So we cannot have that. And likewise, you can't have a times c equals c for a very, very similar reason. So that means we must have a times c equals b. And very, very similarly, that also has to be equal to c times a. And you can get there with essentially the same argument. Okay, so let's put a little box around this. And then we've got one more product, and that is b times c. But as you probably guessed, b times c cannot be 1, it cannot be b, and it cannot be c, because you would run into these same problems right here. So that means it must be equal to a, and that also has to be equal to c times b. Okay, so actually that's all the multiplications that we need for this case. So let's move on to this next case. Again, starting with what's a times c. Well, we've got some possibilities. So a times c Well, we could set that equal to A, but notice that would tell us that C is equal to 1. Just by left multiplying by A again. Oh, but that's not good because we know that C is not equal to 1 because we already have an identity here. Okay, so maybe our next case would be A times C is equal to C. But then we could right multiply by C inverse, and that'll tell us that A is equal to 1. And that's also not a possibility because A is not the identity. But that gives us two possibilities. We could have A times C equal to 1, or we could have A times C equal to B. But now we can do the same trick that we've done before and again, and that is left multiply by A, giving us A squared C equals A, but we know A squared is 1. So that would tell us that C is equal to A. But that's not the case because those are distinct elements in our group. But those are all of the possibilities. A times C could be A, C, 1, or B. Can't be A, C, or 1, so it must be equal to B. So A times C is equal to B. And likewise, we can show that C times A is equal to B essentially the same way. Then off the back of those, we can also show that A times B is equal to C and B times A is equal to C. And that gives us all of our possibilities. Okay, so let's jump to the next board where we have some multiplication tables. Okay, so let's do a bit of a summary here. So we showed that if we started with A squared equal to 1, then that broke into two cases. B squared equals C squared equals 1, and B squared equals C squared equals A. And this is actually related to that second original case that I gave you for homework. That's where this argument for that homework is essentially the same, just in a slightly different order. So what I've done is I've made a multiplication table for this group in both of those cases. And this is called a Cayley table. So let's see what we have. We have A times A is equal to 1, B times B is equal to 1, C times C is equal to 1. And let's recall that A times B is equal to C, B times A was equal to C, and then we filled in the rest similarly. And then over here, we've got the same thing going on. So A times A was equal to 1, A times B was C, A times C was B, and so on and so forth. Notice that in this case, we had B times B was A. Remember that B squared was A squared. Same thing with C squared. And then something that I didn't work out was that B times C had to be 1 and C times B also had to be 1. You can do that using very similar methods to everything that we did. Now down here, I've put two familiar groups with 4 elements. One is Z2 cross Z2, where your addition just happens component-wise. So by component-wise, I mean when you add this ordered pair with this ordered pair, you just add the first entry and then add the second entry. This is happening in Z2, so the only elements are 0 and 1. And when you add, you divide by 2 and keep the remainder. And if you assign A to the element 1, 0, B to the element 0, 1, and C to the element 1, 1, you'll notice that the addition that occurs over here lines up exactly with the group operation that happens over here in ABC land. So that means that these groups are the same. And we've got a name for that. It's called isomorphic. And also there's another name for this group. It's called the Klein 4 group. And then if we look over here at Z4, so that's just like we said before, Zn, but now 4. So you do your addition, divide by 4, and keep the remainder. Well, if you make the assignment A is assigned to 2, B to 1, C to 3, and then you do your addition over here, whereas your group operation over here, you'll notice that the operations line up perfectly, meaning that these two groups are the same. In other words, they're isomorphic. Okay, so I hope you've enjoyed the video. I've got a whole course on abstract algebra, which this video would be a great jumping off point for. It's on the second channel, which is our ad-free learning channel supported by our patrons. It's called Math Major, and there is a link in the description. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.